Hey guys, today you're going to learn about something called equilibrium. So if you look at this chemical reaction, notice that it's a little bit different because it doesn't just have an arrow pointing forwards, the arrow is actually going both directions. That tells us something really important. So that tells us that this reaction is in dynamic equilibrium. That means that the forward and the reverse reactions are happening at the same rate. So when we say forward reaction, we mean the one going this way. So that means the reactants are over here and the products are over here. That's forward reaction. That's like the regular direction that we think about. But then it's also possible to have a reverse reaction. So I'll do that in blue. So a reverse reaction would go this way. So that means that some of the products actually turn back into reactants. So they don't stay products, they kind of go backwards. That's very normal in a chemical reaction actually. Another way to think about that is if you look at this diagram. So here we have a tank of water and I'm pouring lots and lots of water into it, but I'm also letting water flow out of it. This is at dynamic equilibrium. These faucets are at the same rate. So they're putting the same amount of water in as what's going out. What that means is that the level of water in here is actually going to stay the same. I'm not going to get any more or less even though there's lots of water coming in, because there's equal amounts going out. That's what equilibrium means. It's probably going to stay about the same. When you're thinking about this, it means that you're never really going to run out of reactants or products. But there are ways that you can change this a little bit. So we can do what's called shifting the equilibrium. And there are a couple things that can do that. You can shift it by changing the temperature, the pressure, the volume, or the concentration. Some easy ones to think about would be, think about if I changed the volume of this container. If I took this container and I made it a lot smaller, then the level in here, the amount of water would change, and eventually it would even back out, but it wouldn't be the same because the volume of the container had changed. Same thing if I changed the concentration of water, meaning all of a sudden I poured a whole bunch of extra water in here at once. I changed the concentration or how much of the stuff that I had. It would change the level that's in that tank. And again, it would go back to equilibrium, but it's possible to shift or change it a little bit. What you can't do is cause a shift by a catalyst. So remember, a catalyst just makes things go faster, but even if I poured water in and out of that tank faster, I would still keep them at the same rate. So here's what you're going to think about. Say you are a pharmaceutical company and you're making medicine. You don't want to be left with a whole bunch of your reactant. You only want to sell your product to people. So you're going to try to get as much possible medicine from a chemical reaction as you possibly can. The way that we're going to do this is with what's called Le Chatelier's principle. Okay? When we use Le Chatelier's principle, you can shift or you can push the reaction. It will go away from what you add and towards what you take. So notice that this was worded really specifically so that the letters match. It goes away from what you add, so it's got A's, and it goes towards what you take. So this is the phrase that you need to get in your head. This is the super important thing today. Now let's talk about what that means with some examples. So we've got this chemical reaction right here. This is a very common chemical reaction. Notice that it's in equilibrium because of this arrow pointing both directions. So let's talk about this reaction right now is at equilibrium, but if we want to shift it a little bit, if we want to push it, then we're going to use Le Chatelier's principle and change some things. So if I add nitrogen gas, here's nitrogen gas. So whenever you add, the reaction will shift away. Okay, so think about, here's the left side of the paper, here's the right side of the paper. I constantly mix that up. I like to write it out when I do it. So right now it's on the left. Away from this, if I literally draw an arrow pointing away from nitrogen, it is pointing to the right. That means that we say this reaction will shift to the right. Okay, it went away from the side of the reaction that we were on. Okay. Let's get rid of that and let's try another one. I'm going to leave my left and right there. That's going to help me. I don't want to mix that up. So now let's think about if we add hydrogen. Here's hydrogen. Okay. Again, we're going to add. Whenever you add, it's going to go away. It's going to shift away. So draw an arrow pointing away from hydrogen, and that's going to go this way. Okay. Again, that's pointing to the right, so we would say the reaction would shift to the right. In both cases, what that means is if I added either of those, all of a sudden we would make a whole bunch of extra of this product. So if that was a product that you wanted, you could get a lot more of it out by adding those two reactants. That would do what's called shift your reaction. Okay. Let's try some more. This is one of those things that's going to take a little practice and it's going to feel weird, but we'll keep going. So let's think about the next one. If I add ammonia, if you're not sure yet, ammonia is NH3. That's one of those common chemical names like water. Ammonia is NH3. So here's my ammonia. Adding means we're going to go away. So if I draw an arrow pointing away from this, it's going to go that direction. It's going to go to the other side of the reaction. So that means that this would shift to the left. That means I would have less of this and I would get a lot more N2 and H2. Okay? So those were all adding examples. And now we're going to do some removing. Removing means the same as take. Okay? So don't be confused. We want to keep the add and take examples in our head. So now let's think about if we move or if we take nitrogen gas. Okay? So here's my nitrogen. When we take or remove, right? Remove and take mean the same thing. Then it goes towards it, right? So now I'm going to draw my arrow pointing to the nitrogen, towards it. That arrow is pointing to the left. So the reaction would shift to the left, and all of a sudden it would make a lot more N2 and H2. Let's think about the other reactant that we have. Let's think about if we took hydrogen. So here's hydrogen. Remember, we're going to take, which means the same thing as remove. That's what the question said. When you take, it goes towards. So you're going to draw the arrow pointing from one side of the reaction to the hydrogen. That arrow also points to the left. So the reaction will shift to the left and make a lot more of these initial reactants. Now let's think about if we change our product. Let's think about our ammonia, the NH3, right? So there's that. Again, we are taking. I know that we're taking because the question says remove. Whenever you take, it goes towards. So draw an arrow pointing to the NH3, towards it. That arrow goes to the right. So if I wanted to make more of this and shift the reaction that way, I could actually take some away and the chemical reaction would make more. Now the piece that we haven't talked about yet is the heat. But the heat is not actually anything different. We're still going to keep our add and take rules. So let's think first about adding heat. Whenever you add, the reaction will shift away. So let's go up to our reaction and find the heat. Here it is. If we're adding, we're going to go away from the heat, which is that direction. That means that if I increased the temperature, my reaction would go to the left. The way that I know that is because temperature is related to the heat. If I thought about the opposite, let me get rid of that arrow. Now if I thought about removing heat, again, take means the same as remove. Whenever you take, the reaction will shift towards it. So we're going to find our heat and go towards it. So I'm going to put the arrow pointing to the heat. That reaction will shift to the right if I wanted to make more of what's on the right-hand side. So we talked about changing the concentration, the amounts of the things. Now we're going to talk about when you change the pressure and the volume. This rule is a little bit more complicated, so stick with me. So jot these down. If you change the pressure, increasing the pressure goes towards the lower coefficients, where increasing the volume goes towards the side with the higher coefficients. So I know that's a little weird. Let's do some practice together. Same reaction. Okay. I like to write this out a little bit shorter for myself. If I increase the pressure, we're going to go low. If I increase the volume, we're going to go high. Notice that these two things are opposite or inverse. Remember back to Boyle's law, pressure and volume have an inverse relationship. If you can just remember one of these, then you can remember the other one because you know that they're opposites or inverse. So next we need to figure out, like, okay, what's going on with the coefficients here? N2 doesn't have a coefficient in front of it, which means it's a 1. So if I added those up, I would get 1 plus 3. This side has a total of coefficients of 4. Over here we have a 2. Heat doesn't actually get a coefficient. That's not something that we balance, so you're not going to count it in your coefficients. So now I can see which side has higher and lower coefficients so that we can apply the rules. So let's first think about increasing pressure. So think about the y. If I increase the pressure, we're going to go towards the lower side. The lower side here is the 2. If I shift the reaction towards that, that is going, let's put right and left again, don't want to mix that up, then we are going towards the right because that is the side with the lower coefficients. If I decrease the pressure, then it's going to be opposite. Then we're going to go towards the higher side. So if I look at my coefficients there, the higher side is the 4. So if I go towards that total coefficients of 4, then we're going to the left. Now let's talk about changing the volume. If I increase the volume, increasing the volume means that we're going to go higher. Again, the higher side of coefficients is the total of 4 over here, so you're going to go that direction. That is to the left. So that means the opposite of that would be if I decrease the volume right at the y, then we are going to go lower. The lower total coefficients is on this side, so the reaction would shift in this direction, which is to the right. Okay, that's it. There's a whole nother page of practice for you to do to get this really comfortable. Let me know if you have any questions.